What's up, guys? So today we're going to talk about limits that do not exist, as well as global limits. So first off, looking at limits that don't exist, there are two conditions for which you could have a limit not existing with a vertical asymptote occurring at a constant. Two conditions are if the limit of your function as x approaches some constant from the right is positive or negative infinity, or the limit of the function as x approaches a constant from the left is positive or negative infinity, then that means that x equals that constant is a vertical asymptote of your function. So we're going to run through these four examples that you see. First of all, on A, as we approach from the left, you can see that the graph goes down, so the limit is dne negative infinity. From the right, it also goes down, dne negative infinity. Because they both go to dne negative infinity, the limit overall as x approaches c is dne negative infinity, and therefore x equals c is where our vertical asymptote is. Looking at example B, this rational function appears to be headed towards positive infinity. The limit as the function approaches c from the left, well, if we look at the graph, traveling from the left, the graph goes up. Therefore, the limit as we approach from the left is positive infinity, so dne positive infinity. Same from the right. Because they agree, the limit as x approaches c is dne positive infinity, and the vertical asymptote is x equals c. For the third graph, as we approach from the left, we're going to negative infinity. Therefore, the limit of f of x as x approaches c from the left is dne negative infinity. From the right, we have dne positive infinity. Because they disagree, we can say that in general, the limit of f of x as x approaches c does not exist. So where's our vertical asymptote? It's still at x equals c. Even though the two sides did not agree, each of them went to one of the infinities. Therefore, we have a vertical asymptote at x equals c. For the last example, from the left, we can see that our graph is approaching a height of a. From the right, we're approaching a height of b. So the limit of f of x as x approaches c from the left is a. From the right is b. They disagree, so the limit does not exist, and there are no vertical asymptotes. For example 2, we want to think about the graph of this rational function. We know from our knowledge of rational functions that setting the denominator equal to 0 will give you your vertical asymptotes. So x equals 4 is a vertical asymptote. And we can create a quick sketch of this graph. We're going to want that vertical asymptote to occur at 4. So let me draw in my dashed line. There's also a horizontal asymptote at y equals 0. We'll get into that a little bit later. So the behavior of this graph, we want the behavior from the left and from the right of each vertical asymptote. So the limit as x approaches 4 from the left of our function, well, from the left, it looks like it's headed downwards to negative infinity, so dne negative infinity. The limit of f of x as x approaches 4 from the right, and looking at our graph again, as we approach from the right, we're going upwards, therefore dne positive infinity. Alright, so now we're going to take a look at some horizontal asymptotes. Horizontal asymptotes are going to stem from when x is approaching one of the two infinities. They don't always occur. We have a two-part conditional for when we have horizontal asymptotes. If either the limit of a function as x approaches positive or negative infinity is a constant, then y equals the constant is where you have a horizontal asymptote. And we can logically deduce that that means that every graph can only have 0, 1, or 2 horizontal asymptotes. As we go to negative infinity for our first function, we can see that it looks like the graph is flattening out right at negative 1, so that's where we have the limit of f of x as x approaches negative infinity. As we go to the right, it increases forever, therefore the limit does not exist, it's going towards positive infinity. And our horizontal asymptote, there's one of them occurring at y equals negative 1. Make sure you write y equals, not x equals. For this inverse tangent graph, from the left, it appears that we're flattening out right at negative pi over 2. From the right, we have positive pi over 2. If you're wondering where I got the pi over 2's, That's from your trig knowledge. You should know that the tangent function is bounded between negative pi over 2 and pi over 2. So therefore, y is equal to positive and negative pi over 2 is where we have our horizontal asymptotes. The sine function, moving up and down forever in both directions. The limit does not approach a single value. It does not go up forever or down forever. So the limit as we approach negative infinity is d and e. As we approach positive infinity, also d and e. No horizontal asymptotes. So we want to use a table to evaluate this example 4. So what I'm going to do is I want to head towards negative infinity, and I want to head towards positive infinity. So I'm just going to plug in numbers that are gradually getting closer and closer to each of the two infinities. You can see I'm just choosing powers of 10. I'll use those for the negative values. And I can use the same thing for the positive values. So we'll just plug in 10, 100, etc., etc. So when I pull up my calculator and I'm actually plugging in these numbers, let's see what I get. Make sure that your calculator allows you to input x's. You can fix that under the second table set option. You should be able to get these y values out. And we can certainly see a pattern. As we head towards negative infinity, it appears that the height of the graph is approaching 2. As we approach positive infinity, it's also approaching 2. We have one horizontal asymptote, and it's occurring at 2.